This lecture covers the legal aspects of modern surveying procedures. So again, we're talking about legalities, not technicalities. Other courses, other textbooks, they adequately cover the technical processes of modern day land surveying. In this discussion, we'll study the legal aspects of modern surveying. So we got to have a little bit of history and then a little bit of expounding. So land surveyors must be technically competent in the proper use of our surveying equipment. That's a given. We must be more than technically competent. We must also be professionals, which means we must be able to adequately communicate with non-surveyors. So what do we mean by that? Well, just because we know how to compute a position of 3 decimal places and we're certain we have that area nailed down to the nearest square foot, that's really not providing our client and society with value if we cannot explain it and cannot put it into use. Now, this being legal aspects course, we must go ahead and look at the probability that if something goes wrong, the surveyor will have to defend his or her work. That may mean in a court of law, but that's not where you start. You start by having a conversation with the adjacent property owner who doesn't like the results, the client who doesn't like the results. Maybe they're oblivious, but maybe it's the client's attorney or the buyer's attorney. Usually it's not anything that's the surveyor's fault. It's facts that a prudent surveyor has uncovered, discovered, analyzed, reported. But it's something that's negative, so there becomes a polarization effect. Say that you are surveying a piece of property and you find something that's bad about this piece of property. Let's say you're surveying it for the buyer because the buyer wants a new survey to know what they're getting before they close and put their money down. And this adverse condition, say it is an encroachment, say it is an acreage deficiency, say it is the fact that the line is not where someone thought it was. One that I've actually been involved with, all of those, but an interesting one is when a piece of property that was unknown or previously thought to be out of a flood hazard area is now in a FEMA or county jurisdiction mapped floodplain. So the buyer is happy that he knows these detriments and can either renegotiate or walk away from the deal. But now the seller feels like they've been damaged because they thought they had a great piece of property and now they're being told they don't. They thought they had it under contract, was about to close and get their money. Now they're not. The surveyor winds up being right in the crosshairs because if it weren't for the survey, the negativity would not have come out, the detriment would not have been pointed out, and the deal would have happened. So good for the buyer, bad for the seller. I've been involved in several cases where the seller or owner was going after a surveyor thinking that they had done something wrong, which cost them a deal, which incurred financial damages, which is where lawsuits come from. So it's important that besides having it right, doing our job, that we be able to communicate this and explain it. And a lot of that is just communication skill that cannot be taught in a class. It certainly cannot be taught in a surveying class. You might teach it in a psychology or communications class, but the surveyor must be in tune to the fact that we not only have to do it right, we have to be able to explain it. There is an art and a fine balance there too, because surveyors tend to be very analytical and talk over the heads of the non-analyticals in the room. If we're talking with engineers, maybe even architects, we're probably okay. The average property owner, the average finance person, the average attorney, the average appraiser, they're not going to understand as easily as someone who deals in an analytical field. Doesn't mean that they're dumb, doesn't mean that we're smart. It just means that we talk in slightly different languages. So, taking this to the extreme, I'm aware of many property litigation court cases where the wrong side won. And by that I mean, in my opinion, side A was correct. This shouldn't even go to court. This is so simple that even LSIT should be able to understand this, and it should not even, even a basic attorney should be able to understand this. We should not be here. Side B is just causing trouble. Side B just doesn't understand. Side B they're the problem. They're the whole reason we're here. They should not only lose, they should pay court costs. I have saw side B win and side A lose. Tragic, heartbreaking, scratch your head. Why? To some extent, you might say they were out-lawyered or out-attorneyed. You can imagine Ben Matlock could probably win a lot of cases that he had the losing hand on just because of superior legal skills. But what I'm talking about is when it comes down to surveyors being able to testify and explain what we do to the non-surveying element of our society. In this case, 12 jurors. In a bench trial where there is no jury, you got a judge. The judge may be a competent real estate attorney that understands everything that you're saying, which is good and bad, or he or she may be from the criminal prosecution side and don't have any idea what we're talking about, because there's a very minimal amount of property law that's taught in law school and required of attorneys before they pass the bar and eventually become judges on the bench. So we're going to focus on some of the things that surveyors may need to be able to explain besides the particular issues of whatever is going to court. So, from the beginning of surveying, the Egyptian rope stretchers, the Domesday Book in England, the colonial surveyors of the eastern United States, from those early days through the historic period that we last studied, and even into this modern era, surveying consisted primarily of gathering two types of measurements. Not just data, the types of monuments, the instructions of the government or the client. Those are not measurements, those are details and attributes. Surveying consisted of two types of measurements: angles and distances. And obviously I'm not talking about topographic surveys, benchmarks, and establishing grades for railroads and early highways. I mean for property surveys. Angles and distances. Angles and distances may have been measured by a compass, may have been measured by an instrument. Distances may have been measured by an Egyptian rope, a gunner's chain, or calibrated steel tape. We're looking now at the modern era. So, we need to know those footsteps of the past so that we know how to follow them and retrace them. But let's break it down so that once we got into what we call the modern era, we weren't just estimating magnetic declination off of a chart and applying it to a 15-inch long brass navigation compass for a bearing. We were able to do some pretty precise measurements. And even in this current day of the 2020s, we can go back to precise surveying that was done with high precision theodolites and calibrated steel tapes, or early total stations and electronic distance meters, and be able to be those measurements precision wise are on par with what we do today. They just had to go to a lot more work to get it done. So one thing we want to talk about is, on those angles and distances, gathering these measurements forever, whenever a survey was called into question, sometimes the surveyor had to produce the field notes and explain them. whether they did or not, it was expected. Preparation for trial with the surveyor's client's attorney would always include bring your field notes. We got to go over your field notes. If the extent to which property disputes or property discrepancies are explored are usually relevant to the value. In other words, if it's a 3-foot strip of farmland in Podunk County, it's probably not going very far because it's just not worth anybody's time. It's probably worth at most the cost of replacing the fence. If it's a drugstore on Ponce de Leon Boulevard in Atlanta, a foot or two can make hundreds of thousands of dollars of differences and even have profound effects on liability aspects. For example, I was involved with a case on Ponce de Leon where there had been an accident and someone had become injured relevant to a retaining wall. And it became a matter of question, whose retaining wall was it? Because there was a foot or two of error in the surveys in this area. Part of it came from some slop from the 1940s and 50s. Part of it came from some surveying, blundering, idiot mistakes of the current era. So that will go a long ways, depending on the magnitude and what's at stake. So the surveyor, not only did they need accurate field notes to be able to accurately produce maps and plats, to process the data, to go through the steps with the accurate measurements and the good descriptive field notes to create that work product that 99% of the time was never heard from again, never challenged, never questioned, no problem. But they also knew, and surveyors were very aware, that they needed to have all this documented and at their fingertips if necessary, in case it was ever called into question. And sometimes it wouldn't be, hey, we think your survey's wrong, this is going to court. Sometimes the surveyor would come along on the property next door and say, hey, Jim, I got a 5-foot difference on that line, and I don't think any of those corners have moved. I went out there and measured it again just to be sure, and I'm still coming up 5 feet different than you on that 2,000-foot line. Would you check into it? And surveyors just needed to know that. They weren't always looking for a reason to point blame at the other surveyor, but they needed to know why that 5-foot difference was there. Once, was it that this had been measured sloppily? Was there a 5-foot bust in the traverse, and this is where it actually wound up at? Did Jim transpose some numbers? Did he get 97 and 79 backwards on something? The ability to go back in the field notes and explain the survey was paramount. That's what I want to stress. So what were these measurements? Not talking about recording monument sizes and trees and what adjoining owners said. What were the measurements? Angles and distances. In this slide, you can see I took this from the NGS website. These are 2 early EDMs, electronic distance meters. They were mounted to a tripod. Now look at this size of this beast right here on the right, sitting on top of this tripod. This is a tripod and a tribrac, just like we still have today. This was 50 years ago. The tripod and the tribrac have not advanced a whole lot. What we mount to them has mounted a lot. So this was large and heavy. You had to use wood heavy-duty tripods for sure. And then this is what the front of it looked like. And there was, this was the display where the distance would pop up. And this model particularly probably used you see over here on this picture, this cord usually came down to a car battery. Usually had to keep like an outboard motor, like a marine grade boat or car battery to operate these. So here we are with a new way to measure distances. So before long, they figured out, well, we can take this EDM, they can make it smaller, just like calculators started out the size of a suitcase. Now we know how small they are. Computers used to take up a half of a room. Now we know how small they are. They learned how to shrink the technology once they had developed it. So the great big distance meters like the K&E, the Hewlett Packard, the big red one, they all figured out how to shrink those. And eventually, somewhere around 1980, a surveying company or surveying equipment company named Topcon in Japan developed what was known as the Guppy. And to my knowledge, this was the first widely manufactured, affordable total station. Other companies had come out with equally large, but significantly more expensive total stations. Like Geodometer was an early pioneer in these things. But here, the only thing electronic was the EDM. The only thing is the readout right here. That's where it would come out. And I have operated a Guppy GTS 10D. Had a smaller battery, but the battery plugged in, and when you were ready to measure a distance, you flipped the battery on, and that powered the unit. 8 or 10 seconds later, you got the first distance displayed. And that's after you dialed in through the telescope here, focused over here, and looked at the prism, got it dialed in, you get your first distance, and if you were measuring to an iron pin, you would have it in the fine mode, and it would measure to the 100th of a foot. And you'd let it read about 3 times to get a little bit of an average, because sometimes it might bounce around. The technology was early. And if you're just locating the edge of a road, a tree, a house corner, well, you'd flip it into coarse mode. It would measure to the nearest 200ths, and it would measure about twice as fast. But this incorporated angles and distances. So early total stations like this GTS 10D measured what? Angles and distances. So here we're going to stop again and talk about the legalities of the subject matter. Go back to that thought process. Surveyors were very mindful of field notes, being able to explain their work to their client, to a neighboring property owner, to the surveyor of a neighboring property owner, to the client's attorney, to a court of law. Surveyors were often, some of them bore stress and anxiety from this, because surveyors had to be mindful of, we've got to be able to explain ourselves. We have to be able to defend our work. Now, it's surprising to me that as society has become much more litigious, and there's a lot more chance of going to court today than there probably was, at least proportionally, than there was in the 70s or 80s, the requirement to defend our work has become less significant in that legal context. I believe it's because it's not as easy to understand. It's a critical nexus I want to focus on here. The surveyor had been trained. Let's go to 1980 when the Guppy first came out, and it really wasn't commonly found for a few years because surveyors were skeptical. Surveyor could take calibrated steel tape and go measure a distance and look at it and hold it, and if necessary, take a jury out there and lay the tape out on the ground, pull it tight, get the plumb bobs, the tension handles, and measure that distance and confirm and say, see, here's why it's this long. They couldn't do that with an electronic distance meter. So they go, the way that we bridged this consternation where surveyors were reluctant to embrace electronic distance meters there in the 1980s and even into the 90s because they couldn't see it measure. It eventually came down to what I call a process of calibration and repeatability. So surveyors that wanted to embrace and start using EDMs, they needed to know that they were accurate, that they were calibrated, that they would go out on a line that they had measured with a steel tape, and they would measure it with an EDM. And they might make some adjustments. All these early instruments and even the new ones have a parts per million adjustment. That's usually primarily for environmental conditions like pressure, temperature. But it can also be instrumentational error, so that they might use an established distance to calibrate the EDM, and that way they could explain it. Like, I know that line's 450 feet long. I've measured with steel tape. I've gone back with my guppy and I've measured. I've gone back with my K&E bolt-on EDM that weighed 17 pounds, and I have measured it and it came up with 450. So there's the calibration side. There's also the repeatability side, because everybody knew that with a calibrated steel tape, even if you made corrections for heat expansion, you could repeat that distance. You could take two different people, take another calibrated steel tape, go measure that distance correctly, and it was repeatable. There was no doubt that was 250.47 feet long or whatever. So that's how surveyors became acclimated to using electronic distance meters. They became comfortable with the calibration, and that you could repeatedly get the same distance and the same results. And that's how EDM measurements became accepted in court. Surveyors still need to be able to do a brief explanation of how the beam is transmitted from the EDM, how it hits a prismatic mirror, returns back the same path due to the modulation in the wavelength. The EDM is able to count the wavelengths, know how long the beam was gone, divide that by the speed of light, and you have the distance. Simple physics 1. So that's how a lot of modern measurements are done, is by measuring wavelengths and then dividing time by the rate of travel, or the known constant, the speed of light. So this is how surveyors have embraced technology advancements over the last, say, 50 years. Calibration and repeatability. Now, it's worth noting on EDMs that in the 1980s, it was very common for most airports that were open to the public, the local SAMSOG, Surveying and Mapping Society of Georgia chapter, or DOT surveying office would go out with calibrated steel tapes under ideal conditions and measure a long baseline, usually around 1,000 feet. And they would measure it multiple times. They would come up with, this is the distance. We're certain of it. We're good with it. This is what it is. And surveyors would routinely take their EDMs or their total stations to the airport, set up on that baseline, and measure that distance to check it. Sometimes it may have been just for peace of mind, just to make sure that this new black magic technology, the number that it's spitting out on that screen, is actually reliable. Maybe it was just to make them feel good. But regardless, that was hardcore calibration. But that is how we transitioned from measuring with steel tapes to measuring with electronic distance meters and total stations. Similar thing went forward with angles. This guppy is nothing more than a manual theodolite. On the other side of the instrument, if you're looking at the picture, was a little opening that. A little door that opened with a mirror where you could reflect sunlight into it, and we would read the angle off of a vernier manually by turning, dialing this vernier knob right over here, and we would fine tune the horizontal and the vertical angles with these tangent screws, and then we would line up the crosshairs on the vernier looking into the side of the instrument to get the horizontal and zenith angles to record in the field book. So everything was recorded in the field book at this time. But wait, there's more changes coming. So field books eventually gave way to electronic data collectors. So once they figured out that they had displayed the distance that the EDM was measuring on a liquid crystal display, an LCD, wasn't too long until with sine cosine encoders, there was new technology at this time, that eventually became mass produced enough that people could begin to afford it. They started using it on surveying instruments, so that instead of having to look through that peep sight and dial a vernier, the sine cosine encoders were wheels mounted to the plate of the instrument that could very precisely measure how far it rolled around. And some of the earlier ones actually had errors in that they would measure not exactly 360 to a circle. And so that's how they were calibrated, is you would sight on an object, you would rotate the scope 360 degrees, it needed to read 360. Some of the earlier ones did not. They would measure 359, 59, 30, or 360, 01, 12. It would be close, but it would be off. And you had to calibrate and say, no, this is not 360 or 00, 01, 12. This is 00. And so that adjusted or calibrated everything. But we did the same thing with electronic theodolites and the electronic angular display total stations. We went through a calibration and repeatability. Surveyors would go back out to where there was a known angle. I've known of surveyors that set up a point in their office where they could backside a billboard a mile away and turn to the center of a radio tower 3 miles away. Those points were not going to change. That was an angle that was repeatable to 1 second. And they had turned it with a wild T2 theodolite. They had done it with some of the other early theodolites. Some would even get a DOT crew to come by and set up and turn it with a T1, a theodolite developed for really high precision geodetic survey to get that angle so that they could check their electronic instruments. And so that was calibrating it. If you knew that the angle was 84 of 0505 and you set up an electronic theodolite or total station, you better get really close to that same 84 0505 or the surveyor would not trust it. Again, going back to the legalities, why did the surveyors do this? Number one was for repeatable quality results. Number two was so they could explain to the jury how they had established the trustworthiness of their instruments. So once they figured out how to do that and display these angles that were being generated by these sine cosine encoders, somebody realized we're producing electronic data, alphanumeric. Maybe it's bits and bytes, but it was being transmitted from the EDM to the display. It was being transmitted from the sine cosine encoders to the display. Somebody said, why can't we just have it display, transmit this to a device to record it? So on the screen is an early MC5 developed by Corvallis Microtechnologies. And this, to my knowledge, was the most widely used data collector in the very late 1980s and through the 1990s. These things were tough as bricks. One of the suppliers we used to deal with said that, if you forget the hammer, you can always use the MC5 to drive pins with. I would never try that or encourage it, but that was about how it was. These are literally the size of a brick, that you'll see on a brick building. They weighed less than a brick, but not a whole lot less. Probably half or a third as much as a brick. They weighed a couple of pounds. They were pretty heavy. The instrument would plug up to the data collector with a cord. We'd have cord problems, or if the connection got wet, or if one of these pins. You can see there are these 9-pin, if you look here, there are these 9-pin connections on top of the data collectors. Now, these data collectors were not developed for surveyors. There are a lot of different fields that needed data collection devices, like inventory in grocery stores or distribution centers. And we didn't have Amazon distribution hubs back then, but you still had warehouses for Walmart and Kmart and for the grocery stores. Also had them for manufacturing. The avionics. There were a lot of airplanes in the air, and they needed to know where all their parts were and how many they had. So they used these to help collect data on a lot of different things. Thankfully, surveyors could use them too. So often port 1 would go bad, and you'd have to go change the settings and start using port 2. When you got back to the office, you had a cord plugged up to the computer, and you plugged the data collector up using one of these 9-pin plugs. I believe they're called RS-232s. And poof, that's how your data was transmitted. You had to come in here and tell it to transmit, and your computer had to be expecting a file transfer from an external device, and you had to tell it where to put it. Anyway, this is how the early data collectors operated. Now, calibration and repeatability, that's how we bridged the gap. A lot of surveyors were scared to death of these electronic data collectors. What if the battery goes dead? What if it loses the data? What if it glitches and it picks up the wrong data? Keep in mind, at this time, a lot of people had black and white televisions or early era color televisions, and it wasn't unusual for the channel to drift. I can't explain why, but you would eventually get where your channel would become fuzzy, and you'd have to go have a little adjustment dial and dial back into the station. So this was the life that we lived in at that time. So there was reluctance to accept electronic data transfer. What if it drifts off? What if it drifted off? How will we ever know? How will we defend to a jury why this angle's 3 degrees off, hypothetically? Fear that we'd have a 3-degree blown angle brought into the office because of this. Calibration and repeatability. I have personally, and I've known of several others who for the first few months, sometimes a couple of years, the advantage of the data collector was not in collecting data, it was in entering it. So before the data collector, all the angles and distances had to be written into a field book with a pencil. Assuming that we're talking about the computer era, all that data then had to be manually entered, one character at a time, into the computer to create a raw data file. So there's a lot of time involved, There was also room for human error. The fat finger could kill a survey and you'd never know it, or you'd figure it out later. So one of the first advantages was the time involved. For example, I think of a 40-acre field topo that I prepared in the late 1980s, maybe around 1990. Took about 7 days in the field. Took about 2 days in the office just to manually enter all the field data into a raw data file so that it could be reduced before we ever reduced the data and had a closure to check or could start plotting points. So that was the advantage a lot looked at. They did not trust it. So we would collect the angle and distance with the data collector, and then we would manually enter it into the field book. And we would compare in the field. Yes, that's correct. Yes, that's correct. So eventually, after you did this long enough, if you were in the field, you knew that it was not giving you bad results. What it was collecting is what it was observing, and that it was reliable. But to the sage old surveyors who came up with a 1-minute transit and a steel tape and a field book, it took longer to convince some of them. Of course, if some of them didn't care, they embraced it immediately and took off with it and benefited from it. But the sage old surveyor, the responsible professional, was able to look at the jury and say, I know that's the angle that was collected because we have tried it. We have found it to be we have calibrated it. It collects the same type of angles, and it's repeatable. It collects the same angle time after time, just like a field book would. And that's how, a lot of surveyors were just scared to death. How do I produce field notes? Well, I guess in the early days, I know for a fact it was a printout of the raw data. So that's how we got there. And of course, this all evolved from, at this point in time, we're looking at electronic total stations and data collectors. And now we've advanced all the way as far as angles and distances to the robot. And this is a typical one. This is a commonly found robotic total station. As you know, the guy on the other end, it's all Bluetooth, it's all wireless, there are no cords. In this case, there is no instrument operator. The instrument tracks the rod man, or the technician, collects these angles and distances, just right here like we want, from the, down to the second. And so again, we've got there by calibration and repeatability. We've taken total station measurements and checked them by robotic total stations and found that it's the same. They are, they're all calibrated the same, and the results are equally repeatable. So that's how we've gotten through the modern era in total station, or in angle and distance measurements. Now, obviously, we did not touch on GPS, which is a whole different topic we'll jump to next. The takeaway here is, as technology has advanced, surveyors have had to prove and be able to explain the technology. This is how an angle reads out a distance. There's a little sine cosine encoder wheel that's mounted to the top of the plate of the instrument where it turns around, and that computes the angle and displays it. That's adequate to explain to most non-surveyors. That's easily enough to understand. A little brief explanation about how an EDM transmits a beam and then computes a distance. That has not changed since the 1970s, when EDMs first began to be widely used. And they weren't very widely used then, really, until the 80s. So be able to explain it so that the jury can understand, because in the legal world, the other side may think that if you can't explain that, they have discredited you. And that has happened. And that goes back to what I said at the outstart. Sometimes the winning side loses because of how poorly the surveyor was able to explain it. If the bad surveyor with the bad result on what should have been the losing side can make eye contact with the jury and explain, this is how an electronic distance meter works, I know, I've tried this, and give them a simplified explanation of a wavelength and the speed of light, and that they've gone out and checked these distances over and over against established distances, and they know it's true, and this is how all the data is collected, the jury will find more confidence in that surveyor, even if he's not very competent at all, than over a brilliant surveyor who can explain things to 3 decimal places, but does so in such a way that nobody can connect with him or understand with him or her. So that's the takeaway. Be able to explain the generalities of the technology to the non-surveyor. You got to understand how the equipment works anyway. Otherwise, it's really irresponsible. That's the difference between a technician and a professional. A technician does what he or she is told, doesn't question much. They're very good at performing a skill. A professional understands what happens when they mash the button. They understand what happens when they do this or do that, and the why, and they're able to explain it. That's the difference. That's where we are. We'll move next to a discussion on GPS. It's a very similar legal prospect, but technology, it's very different.